Welcome to the lecture number 15 of this course, Basics of Fluorescence Spectroscopy. In lecture 14, right, so what we are discussing is the solvent effect of fluorescence, and in that regard what we have seen is that Lippard-Matlack equation, right. And in that Lippard-Matlack equation, what ultimately we have seen is that if we take the fluorescence spectra of your molecule, right, as a function of different solvent, and then function of different solvent is given by the two quantity is dielectric constant and the refractive index, where the orientational polarizability is expressed as epsilon minus 1 by twice epsilon plus 1 minus n square minus 1 by twice n square plus 1. So, in that case we will get a straight line, and from that slope we will be able to calculate the excited state dipole moment if ground state dipole moment is known, or ground state dipole moment if excited state dipole moment is known, provided that A, that is the radius of the cavity, is known to us priori. So, then I argued that okay, so if we want to measure the excited state dipole moment, then from some other technique, right, we need to know that what is the value of the ground state dipole moment. Obviously, those techniques are available, but what I wanted to show you today, that if we, and eventually we have started the last day, that if we just rewrite the equations, right, which we have already derived in a different form, then the situation which will come will be so interesting that we will be able to measure the ground and the excited state dipole moment together, right. So, in that regard, what we ultimately got is these two equation. The first one is that nu absorption nu bar, right, minus nu bar emission is equal to twice mu E minus mu G whole square by HCA cube, right. Here this C is because it is in the wave number, into epsilon minus 1 by twice epsilon plus 1 minus n square minus 1 by twice n square plus 1 plus that C, right, that C is for our inherent Stokes shift in the molecule, right. And also we have seen that if we take this nu bar absorption plus nu bar emission, right, then what you will going to get is minus twice mu E square minus mu G square divided by H C A cube into epsilon minus 1 by twice epsilon plus 1 plus n square minus 1 by twice n square plus 1, and we will get some other constant, right, C prime. So, here what you can see, this first one is nothing but Lippard-Matlack equation, right. The first one is nothing but Lippard-Matlack equation, and the second one I just did that nu bar absorption plus nu bar emission. So, in this case what we are going to get is a negative slope, right, negative slope. So, let us write this as this is equal to, let us say this is equal to m1, right, that is my slope, epsilon minus 1 by twice epsilon plus 1 minus n square minus 1 by twice n square plus 1 plus C, and this will going to be equal to minus m2, only this function will be different, here is minus, but here will be plus epsilon minus 1 by, right, plus C prime, right. So, now if I plot these two, the first one is nu bar absorption minus nu bar emission, then I will get a line like that way. So, slope will going to be this one, right, and if I plot nu bar absorption plus nu bar emission, then you will get the line like this way, and here slope will be equal to m2, right. Now, I can tell you that one formula, right. Let me write one formula over here, and if I put this value and we will see what will come, right. If I now calculate m2 minus m1 divided by 2 into HCA cube by twice m1 to the power half. If I write that, then I know the value of m2, the value of m1. m1 is twice mu e minus mu g whole square by HCA cube, like that, and m2 is twice mu e square minus mu g square by HCA cube, like that. So, I can simply plug in all the value, all the expression of m1 and m2 in this equation and simplify it, right. So, that you can just write it over here. So, m2 is twice mu e square minus mu g square by HCA cube minus m1 is twice mu e minus mu g whole square by HCA cube. That whole thing is divided by, so this is, that whole thing is divided by 2, and then I have this quantity, right, HCA cube divided by twice m1, no. So, then m1 is twice mu e minus mu g square by HCA cube, right. I have this. If I simplify this, what you will going to see is this is nothing but mu g, that you can do it later. So, upon simplification of this expression, what you will get, this is equal to mu g. That means if I know these two slope, right, this slope, this m1 and m2 separately, right, then what I will going to get? I will get this mu g. Once mu g is known, right, mu e will be known automatically. So, there is no problem. So, we can measure the ground and excess dipole moment by using the solvent dependent change in the fluorescence spectra, right. Okay. So, as you can see that in this plot, right, in this plot, so here is my nu bar absorption minus nu bar emission versus that F var. Typically, we will write F var, and you know that this is a function of dielectric constant and refractive index, which is nothing but epsilon minus 1 by twice epsilon plus 1. Like this form, right. So, for different molecule, right, this feature will be different, right. So, for some molecule, if this feature is like this, for the other molecule this feature may be something different, is something like this, right. So, looking at these two molecules, let us say the molecule here what I am drawn, the dependence is this molecule, and this molecule is this one, right. In this case I got the slope is more compared to the other, right. It simply means that the change in the excited state dipole moment from the or the change in the dipole moment, that means mu e minus mu g is more for the molecule this one. So, mu e minus mu g is high, that is change in the dipole moment is more where the dependence is more, right, where the dependence is more. Okay. So, while discussing this, I have taken one inherent assumption on this. What is that assumption? The assumption is this solvent, right, will create a reaction field because of the induced dipole moment by the solute dipole, right. So, induced dipole by the solute dipole, it is the it will create a reaction field R, right, and then we use that R for the derivation of this Lippert-Matlack equation and the extension of the Lippert-Matlack equation. But we have not explicitly said, but it is true that we have not taken into account any specific solvent interaction. If there is any specific solvent interaction, that means the solvent is actually interacting by hydrogen bonding or any other means with the solute molecule, then all this description of this solvent dependent emission spectra or solvent dependent fluorescence are not going to be correct, right. So, this whatever I have discussed, this Lippert-Matlack equation is under the condition that the solvent will not going to have a specific interaction, right, solvent will not going to have a specific interaction with the solute molecule. So, this is true when there is no specific solute solvent interaction, right. If there is a specific solute solvent interaction, let me show you one molecule. This specific solute solvent for this molecule, this is a very famous example. Right. This is for this molecule. If you change the solvent, right, this solvent is let us say ethanol water mixture, right. So, you can tune the radiality constant and refractory index nicely. So, in this case the change in the emission spectra of this molecule will be enormous for very low concentration of ethanol, right. If I may draw briefly over here, this is that lambda, right, emission, and this is my intensity of fluorescence, right. I can represent as I or F, whatever you want. So, when it is like pure water, what you will get, this emission is something like this, right. This maximum is around, here is around 400 nanometer, here is around 450 nanometer. With a very small amount of ethanol, this spectra will shift, right, drastically. So, a small amount of ethanol, this spectra will shift to like this, only 3% of ethanol. Now, if I change the ethanol concentration to 100%, there will be not much change in the emission maxima, right. So, when I change this to 100%, this will be something like this. That means somehow this molecule is interacting, with ethanol, and in this case we cannot apply this Lippert-Matlack equation for this molecule. So, specific interaction has to be should not be present, right, between the solute and the solvent. Then this Lippard-Matlack equation is valid, and we can easily measure the ground state dipole moment and the excited state dipole moment, right, using this solvent dependency of the emission or fluorescence spectra, right. There is another catch over here, another condition over here. That condition, let me write it or let me explain it using this diagram over here. So, this is my ground state of this molecule, right. Let me write it as S0, and I have excited this molecule H nu absorption, and I have created this excited state. This excited state, so here is my H nu absorption that we already have calculated over here. This excited state will stabilize because of the solvent reorientation, right, that we already have seen, and then that is why this F over is applicable, right, after when I am talking about this emission part. So, let us say this is my stabilization till here is my stabilization. My stabilization, and then emission is taking place from here, lambda emission or H nu emission, H nu emission, right. Now, from here to here, so coming from this state to this state, right, there will be a numerous number of steps depending on the specific solvent reorientation around the solute dipole. If this process is much faster than the lifetime of the state, lifetime of the state is about nanosecond that I have said. This is about 10 to the power minus 9 second. And if this process starting from this state is 1 unsolvated, right, and this S1 solvated. So, from this to this state, if the time scale is much faster, then this emission, right, will be provided only by this stabilized energy state. If this process, if from here to here, if this process, right, if this process is slower, right, then from each and every state will contribute to the fluorescence. So, whatever I said, this is true when I have this process is much faster than this process, right. So, in bulk water, right, in water or in this process is about picosecond, 1 picosecond. In methanol is water. In methanol, this is about 4 picosecond. So, obviously, this is about 1000 times faster, right, and so in for every day I have no issue, I can get these things done. But if you use a viscous solvent, right, like ionic liquids and several other viscous solvents are available. If you use a viscous solvent, then this emission, right, will also get a contribution from these different intermediate states. Let's ask the question in a different way. If you really want to get the information of this state, that means what you are going to see is emission at 0 time from here, nothing has been solvated, no energy minimization because of the reorientation of the solvent. After some time there will be little bit reorientation of the solvent. So, now the emission will be not this much of energy, but emission will be like this much of energy. After some time emission will be this much of energy, and at the end emission will be this much of energy. It means that with time the emission spectra will shift towards the longer wavelength or red side, right. So, it means that if you can somehow take the or if you can somehow measure the emission spectra as in a time resolved mode. That means, immediately after excitation, if this is my emission spectra, after some time, that could be 1 picosecond, that could be 100 femtosecond, that could be 1 nanosecond, depending on your system. If you can measure, then what you are going to see is that the gradual shift in the emission spectra, right, gradual shift of the emission spectra as time goes. So, basically what you are going to see is the following: time resolved emission spectra, right. So, initially at early time your emission spectra is something like this. As time goes, emission spectra will shift to the longer wavelength. Here is my wavelength axis over here, and here is your intensity, right. As time goes, your emission spectra will shift, and when things are at this position, then there will be no longer shift. Then even you change the time, there will be no longer shift. That means what I said, this is T1, let us say, this is T2, let us say, this is T3, this is T4, this is T5. Here T5 is greater time than T4, greater than T3, T2, T1, right. Here these emission spectra are different, but for these two emission spectra are very same. That means it has reached this my fully solvated state. That means after that time there is no longer any solvation taking place. That means it has reached the most stabilized state, and that state what we have seen in our Lippert-Mataka equation, right. So, now question is that if I want to get such kind of time resolved emission spectra, right, then that normal steady state emission spectra is not good enough, right, because that will going to give me the integrated value of all these emission spectra, right. That will going to give me the integrated value of all these emission spectra. So, my question is how we are going to get that, how we are going to get this time resolved emission spectra. If I will be able to measure the time resolved emission spectra, I will be able to see the formation of this state through the intermediate states, right, and that is a very interesting topic, and the time scale of going from this state to this state, right, is known as the solvation time, right, and the dynamics is known as the solvation dynamics, right. So, eventually by this we will get the solvation dynamics of the solvent of your choice, right. As I said that in water it is about 1 picosecond, and as you change the solvent to methanol it increase, right, 4 picosecond, 5 picosecond, right, and so on and so forth. Okay. So, now let me briefly discuss this thing, that how we are going to measure this time resolved emission spectra. Okay, so I think the time is almost up. So, before starting that how we are going to measure the time resolved emission spectra, let me repeat what I said using a diagram. That means that when I excite my system from here to here, these are my intermediate states, right, that is what, and this is my final state, fully solvated state. So, every time I am going to measure, I am going to measure the emission like this, right. So, here I will get emission spectra like this way, and in this case this will be shifted to the red side, and after some time this will remain same. Okay, as time is up, so I will finish here, and in the next class what I will going to do is I will show you that how we will going to calculate this time resolved emission spectra from the measured emission intensity as well as the lifetime measurement. Earlier what I said you that the 4 different parameter of fluorescence, right, you remember I said that the intensity, I said the quantum yield, right, I or f. So, this is denoted by phi f. I also said the emission maxima, generally denoted as lambda emission max, and I also said the lifetime, fluorescence lifetime, right, this is denoted by tau f. And I also showed you that this tau f is nothing but 1 over Kr plus K Nr, radiative and non-radiative process pathway. So, but I have not told you that how we are going to measure this lifetime, right, and this is important to get this time resolved emission spectra. So, we have to measure the lifetime, right. So, the measurement of lifetime is important in our case. There are two ways we can measure the lifetime. The first one is in the frequency domain measurement, and the second one is the time domain measurement. I am not going to discuss the frequency domain measurement in this course, but I will discuss the time domain measurement in this course. In time domain measurement, the idea is very simple, that you excite your sample with a short light pulse, and now let us monitor the how the fluorescence intensity will change as a function of time, right. And with this, let me finish here, and we will continue on the next lecture. Thank you very much.